everyone, it's Judy Warner. Welcome back to this second episode of our special series created between Keysight University or Keysight Learning and the Ecosystem Podcast. In this episode, I'm joined by expert Steve Sandler, Managing Director of Picotest, and Heidi Barnes of Keysight. We're going to talk about power integrity, power delivery networks, and where we've been, where we are, and where we're going. You're going to learn a lot from these two experts that are always at the leading or bleeding edge of these technologies. Make sure you go check out the show notes when you're done. I put lots of links and resources for you there. Now let's jump into our conversation with Steve Sandler and Heidi Barnes. Hi, Heidi. Hi, Steve. Thanks so much for joining today on the podcast. It's great to see you both.
Nice to be here.
Great to be here with you.
Well, why don't you take just a quick moment and tell our viewers and listeners about who you are in case they don't know you.
Ladies first.
Thank you, Steve. And it's a pleasure to be here with Steve. He's the one that got me involved with power integrity, and now I am actually the product owner for power integrity with Keysight's Pathwave EDA simulation tools. And it's been a great privilege to be working with Steve and to be doing this podcast today. And Steve, your turn.
How far we've come since 2015 when we first started working together, and it's been a blast. So I'm having fun. I'm Steve Sandler, Managing Director at Picotest, and we specialize mostly in measurements that have to do with power electronics, power integrity, and everything between those.
Okay, so that was the easy part. Now I'm going to ask you a question. I'm sure you've heard it many times, but I don't know that our audience has heard either of you say that. So how would you define power integrity?
That's an easy one because it's in almost all of my keynotes. Power integrity is the science of getting power to devices that it likes. And that means different things for different kinds of devices. And some devices are more sensitive than others, but our job in power integrity is to make sure that we've optimized the power for the devices that we're powering so that they can work at their peak performance.
I like that.
And I
Heidi?
kind of like to add to that. Steve, very simple. I work with a lot of high-speed digital applications. We talk about power delivery. Power integrity is the delivery of power to high-speed digital loads. The one that I've more recently come up with is power delivery is not DC, it's AC. So, DC resistance, IR drop is important, but power integrity is really about the impedance involved in delivering power to a load, because the load is not DC, it's AC. It's a dynamic, highly, dynamic currents. And for that matter, that's why EM simulation is so important. We need to use an EM simulator to get that impedance right and really look at how that power is being delivered to a dynamic load.
Yeah, good point. Good point.
I think that's a great explanation. So, Heidi, you're at Keysight. Steve, you and I have talked many times, and I know that you happen to be an ADS expert that you just basically jumped in many years ago. So what does it take to simulate power integrity? You touched a little bit on that, Heidi, but what else would you say that it really takes to get good, accurate measurements?
It's so much easier than it used to be. You're right. I kind of jumped in 2009, actually 2008, I think. I got my first ADS simulator. And even since then, it's gotten so much easier. The interfaces are much more intuitive. So it used to be very complicated to, get all the settings for meshing and momentum settings and all that stuff. And now most of that is automated. So, there's a little bit of a learning curve to learn the interface of the tool and where the knobs are. Other than that, it's really very easy to use. You import the printed circuit board. You define where the power supplies are, you define where the loads are, and the rest is pretty much automatic. In fact, even now, ADS can help you pick the right capacitors. It can help you tell where to put the capacitors. It's really, almost intuitive, I think. And it keeps getting better. So every year it seems like it has both more capability and also becomes easier to use. That's a great combination. And I am a certified expert now, and I'm very proud of that.
And Keysight's very proud to have you as our certified expert for power integrity.
Yeah, thanks.
Well, early on, I think it'd be an interesting application to talk about, Steve. I remember, I'll never forget the first time I interviewed you and didn't really know much about your background. And the first thing that comes out of your mouth is you casually start talking about modeling the power on the International Space Station. So for our listeners and our audience, why don't you touch on that, how sort of what took you down this career path and your experience on the space station?
I think we get most places accidentally, and we get led through experiences that land us somewhere. And I happen to be working for a company that specialized in satellite electronics. I've been in satellite electronics almost since the 1970s. And they happen to be the major subcontractor for the space station. And they asked me to consult on the space station, which I was happy to do. And so I spent a lot of time in Palo Alto in those days. But one day I overheard a conversation between the subcontractor and NASA, and they were trying to decide how you could do the worst case analysis of something that was as big as the space station. Nobody had ever done it. And it was around Christmas time. So I went home and I came up with a business plan to build a company to do the worst case analysis of the space station. And I submitted it as an unsolicited proposal and I won. And, poof, overnight I had a company and I had 7 people working on space station. We spent 6 years creating those models. I think I delivered a little over 300,000 pages of analysis in 6 years.
Unbelievable.
And it was crazy. To this day, I can't tell you if winning that contract was a good thing or a bad thing. But I think it was probably a good thing.
I think most of us would agree it was a good thing.
Yeah. Well, it makes for good stories on podcasts.
I just overheard people saying that they didn't know how to do this. And I was thinking, well, it's not that hard.
Says Steve Sandler.
Right.
So I heard you say one thing is that what was interesting about that is that in regards to that application, you had to be right? And
Yeah.
it seems like, knowing that, what kind of pressure did it put on you and what did you learn and grow through?
We learned a lot. Yeah, we learned a lot and we studied a lot. And I would say that wasn't really anything new. I've been in the satellite business a long time. And the mentality always was that if we're wrong, really bad things happen. And people point to things like the Challenger and we remember when things don't really go well. So the motto was be right. And the very first thing we did when I started the company to do the analysis of the space station was to figure out why things are wrong and what makes them go wrong. And that was a very interesting process. We spent about a month and a half doing that. And we found a few things. One thing we found is that most errors occur during data entry. And so like if you have 100 engineers and they're all typing in the tolerances for a 0.1 microfarad capacitor, they tend to type in different numbers and they don't always get it consistent. And so one of the first things we did in Space Station is to create databases that were locked and protected databases so that you couldn't type in those numbers. They had to be retrieved from a database. And so long as everybody pointed to the right part number, everybody got the same answer. That was one thing that we instituted. We instituted other things too. For example, every piece of paper that left AEI Systems was reviewed by at least 2 people. And that was true even if I wrote it. There were 2 people that read everything that I wrote to see if we could make sure that they were right. Every simulation that we did was tied to a measurement of something. So we never took anything for granted, even a data sheet, whatever it was. We had to have a measurement that proved that our nominal was right. Because what's the point of doing, worst case of Monte Carlos of something that's not nominally right? We had to be nominally right. And so we did things like that also. And that's actually become a lot more sophisticated over the years. We used to, just put the simulation and the measurement on the same page and you'd look at them. And now we have sophisticated tools that put them into the same screens and rescale them and things like that. So we can actually see even minute differences. But the rule always was be right. And it's really fascinating when you look at the world of satellite systems today and you look at the SpaceXs and it's mostly just experiments, right? And everybody says, wow, look at that. They landed vertically and they did. But if you look statistically at their performance, it's relatively poor. it's maybe 90% successful at this point, which is somewhere around 1 or 1.5 sigma. And in satellite systems, we're looking for 6 sigma. So, yeah, it might be pretty good by industry standards, but certainly not by space standards.
And I was going to add, out of, I think, your aerospace work and working in that industry, you came up, as you mentioned, you do simulation and measurement. And I think that's one of the great things about working with you, and also, learning to do those power integrity measurements, learning to do the simulations that are needed. But one of the things that came out of that work in the aerospace industry was the non-invasive stability margin measurement and methodology, which allows you to determine or check, validate the stability of a power supply for an aerospace application, and do it non-invasively. You don't have to open up the control loop. And I think you learned very early on that in the practical world, you can't always access that feedback control loop of a power supply. And so NISM's a wonderful thing, and very excited. Steve just released with Keysight video on non-invasive stability measurement or margins and measurement and simulation.
Yeah, it's really interesting how that came about. We wanted to get these measurements, but they weren't really available on the circuit board. So, I happened to be up in Palo Alto, and NASA was there, and I said, "You guys happen to have an X-Acto knife?" And they said, "Why?" And I said, "I'd like to cut these boards up a little bit so I could make access for the control loops." And of course, everybody flipped out about as much as you would expect they would, right? And no, they weren't going to give me an X-Acto knife. So that's actually how that came about, is that I realized we needed some sort of a way to make these measurements without having to cut the traces on the circuit board. And it's been pretty good. It's been around now for almost a dozen years, I think it is. And it's adopted pretty widely across the aerospace industry and even at NASA. So we're pretty proud of that. But I think that, one of the things that progresses, if you look at how we do our measurements and how we do our simulations today versus how we did them back in 1999 when I was doing space station, things have evolved so much. And I go back and I read those reports now, and all the assumptions were very carefully written, to make sure that we said exactly what we did and exactly what we didn't do. And almost every one of them has this note that says, and it doesn't include any printed circuit board effects. And today I would say, why bother, right? I mean, it's all printed circuit board effects. And I still see that occasionally in reports from AEI that, it's only 10 megahertz, so we didn't need to worry about the printed circuit board. And it's amazing how low in frequency printed circuit boards get in the way.
Yeah, I remember you saying that to me one time. And for me, coming from the board industry, it felt so lowly, compared to some of the high science things you do. And I'm like, hey, boards, I'm relevant again. This is awesome. Because I know something about circuit boards. But when you get up to those speeds and frequencies, like you said, everything matters. Yeah. So that's a bit of sort of where you've been in the past. That's power integrity past. Where would you say we are today? What are some of the challenges? What are some of the drivers of the technology?
There's a lot happening. Speeds keep getting faster. And, 200 gigahertz stuff going on in millimeter wave. And, I had a conversation with Al Neves just the other day. And it's like, he starts at like 50 gigahertz. And so there's, that craziness going on. Transceiver business is really, really booming, trying to keep internet speeds up. And so there's a lot of high-speed work going on there. The focus on power has really been towards bigger processors. And you see it, AI is consuming tremendous horsepower. Social media. In fact, I had a conversation just 2 weeks ago with an investor, and he casually mentioned that the number one consumer for H100 boards from NVIDIA is TikTok. And that blew my mind.
Did you see that one coming, you guys? I didn't.
I did not. But all of these big companies, they're all, creating these tremendous horsepower data centers, AI centers, HPC, and the requirements that puts out are incredible. You talk about printed circuit boards, and now we have people doing chips at 2,000 amps. I have one customer that's doing a chip at 5,000 amps. And to get that across a printed circuit board isn't so easy. And I think it was just yesterday we got an email telling us that our DesignCon paper for this year was accepted. And we're doing a paper on the design, simulation, and validation of a 2,000 amp core power rail. And
Oh
you think
my
about that,
gosh.
and it almost seems casual on the one hand, right? Because we've been getting there for a long time. And then other people say, it's crazy how far we've come. But I would say back in, I think it was 1976 or 1977, I had a part-time job at a power supply company while I was in high school. And we were building 1 volt, 2,000 amp power supplies for IBM back in the day. And what I would say is they were a lot bigger than they are now.
Yeah.
And maybe now they're a lot more sophisticated, but there's always been this fringe. And what's happening, I think, is the fringe is moving closer. It's almost mainstream now to be doing 500 or 1,000 amps, which is kind of crazy to think about. And when you look at the ramifications of that, it's not only developing a 5,000 amp power supply and being able to support the impedance that it takes for that to do its thing at 10 gigahertz or whatever it's switching at. But you also have all of these signal integrity channels that somehow you have to not bother while you're doing that. And so containing EMI in sockets and trying to get power through the board and get the planes as short as you can get. I mean, getting power modules to the point that they fit, it's all challenging. Migration to 48 volt power systems, it sounds really easy and there's a lot of benefits to it. Higher efficiency, lower conduction losses. But I'm doing an EDICon session on the migration to 48 volts. And one thing people don't think about is that we don't actually have the equipment and tools for it. Power rail probes are really great, but they don't go up high enough to support data center and AI. They don't have the dynamic range for data center and AI. So two-port impedance, we've mastered that. We know exactly how to do it, but we don't know how to do it at 48 volts. And so all of a sudden, the challenges that are placed on new measurement technologies and instruments are becoming really challenging, but also fun.
So Heidi, how are you going to do this? How do you develop tools?
Simulation's a little bit easier because when I hit the wrong button, it doesn't melt down and burn up in front of me. So,
That's true.
so actually, simulation's becoming very important because you really do want to get it right, the first time, and not have dramatic failures or very expensive failures late in the design. So one of the things I think Steve brought up earlier was how the automation that we're seeing in the EDA industry is really helping. We have Power Integrity Pro, PI Pro, that's targeted at optimizing the EM simulator for simulating the power delivery network of a printed circuit board. And as Steve mentioned, it makes it really easy to identify the source of power, the VRM or your connector input, identify your sinks, the switching DC to DC converters, and you're up and running with because it recognizes the nets, it can find components, makes it easy to add models. So you can be up and running in a matter of minutes and figure out what's the impedance of my power delivery network. And then the thing I think that I learned a lot from Steve was you don't just stop there with the EM model. You have to look at the end-to-end PI ecosystem. So a lot of our collaboration, and most recently with Ben Dannon of Northrop Grumman, and then also a lot of our work with Jack Carroll of Xilinx, has been looking at how do we model that power supply with the state space average model that's been developed by Steve. How do we model the dynamic load, and how do we bring that all together into the simulation of a PI ecosystem and look at the actual transient steady state noise ripple on the power rails. The one thing I should add most recently, and I think Steve just mentioned, we have the world of the supercomputers and these massive designs requiring thousands of amps. And that's one challenge with thermal and, very low impedance down to the microohms. But we also have the AI world or the autonomous vehicle world where you're seeing such a high density of electronics that they have to play nice together, okay?
Yeah.
The noise from one power rail can't contaminate the other power rail, and yet they're all connected because they're all coming from the main, one source of power. They're all using sort of the same ground. It's this giant interconnected web of power and ground, power delivery network type thing. And you can't let conducted EMI get from one system to another. And that's one of the things with the automotive industry. They have some of the strictest standards for conducted EMI and radiated EMI. And so that's one of the things we've done recently in our power integrity EM tool. We have an analysis where you get everything working with a DC IR drop, a simple, a setup you can understand. And then the automation is you can just copy to a conducted EMI analysis where it will set up the ground reference plane just like in a conducted EMI measurement, and it does the differential setup of the ports, and it adds an actual switching model, a simplified switching model for your DC to DC converter, which is oftentimes the source of the EMI noise, and then it runs your simulation for you. So there's a lot of automation there that really helps the power integrity engineer get up and running and doing some pre-layout design work before they actually start fabricating hardware.
Yeah, and some of the leading advances really are in the automotive industry now, right? I think they're kind of paving the way in simulation.
Well, that's always the benefit, right? Is that we get out over our skis a little bit technologically, but it's like the rising tide raises all boats, right? Then we got to fix the whole ecosystem around it, right? And I guess that's a good thing. So
I think it's a good thing. Yeah. And so now I think the next limit is the semiconductor companies that actually make these power modules that really don't understand too much about power integrity of their applications. So, I think we did a paper at DesignCon with Texas Instrument last year. This year we're including monolithic power systems in our DesignCon paper. I'm working with Analog Devices for the Supercomputer Conference in Denver in November. And so I think that the semiconductor companies are coming around and they're starting to realize that they need to get their act together because they're the ones that are at the very front end of the power delivery network, and they don't quite understand what it means to get that right. But they're at least starting to engage now, and hopefully by engaging, they'll learn what they need to know, and they'll start helping us get what we need. And as a result, everything gets better. It gets better for everybody. I think that's how it happens. It's like you said, everybody gets a little bit over their skis, then we play catch up because we realize we made a mess and we got to go clean up our mess.
Right, but
I think that's the way it goes.
Yeah, exactly.
And so we're excited about where things are going. We're excited about being at the Supercomputer Conference. It's the first time we're doing that one, and it was actually on the recommendation of a financial advisor that happened to see us at DesignCon, and he said, "You need to be at the Supercomputer Conference." And so we decided we would go booth and show off the coolest stuff for the data center and AI world that we're so heavily involved in, and that's just the way it goes, and it'll keep ratcheting until it reaches some equilibrium, whatever that is. But the equilibrium never gets reached because everybody's still striving for more, right?
Yeah. And we didn't really mention it, but 2,000 amps sounds crazy, and 50, 200 gigabits, all this. But the one little piece in there that also is mind-boggling to me is that our SERDES, our serial digital data transmission, they're going multi-level. So where we had ones and zeros, now we've got, PAM4, they've, some crazy ones, PAM16. But when you start splitting that up into multiple levels, you just reduce the amount of noise margin that you allow on each one of those levels because they can't interfere with each other. And that means we have less margin for our power rail, and they're requiring a lot more stringent, smaller noise levels on the same, power rail voltage that we maybe are used to in the past, but now the margins are getting much smaller.
Yeah, you're right. The margins get tiny. And so one of the things that we're introducing at the Supercomputer Conference is chip emulators, so we can emulate these 2,000 amp chips so that we can directly measure those margins at package speeds. And, switching around 2,000 amps at package speeds is a little bit of a challenge. But, I live in the world of crazy, so it sounded like fun. And it sounds a whole lot better than risking $10 million chips to see whether or not you got the power right. No, that chip's dead. I guess that one doesn't work. That's probably not the best way to do it. And so we'll be able to do these emulations. We'll be able to make direct measurements, and we'll get the power of the simulator, which isn't really in getting that initial simulation. The power of the simulator is being able to get the optimization. And so what I tell my customers, you're investing so much money into your ability to do simulations, not because you want to just sit and do simulations. It's because eventually it matters, right? We don't know when it matters, but eventually it matters, and we need to get it right.
Steve, I know Picotest did some exciting things, which I think you'll be showing off pretty soon. Did you want to give our listeners a little sneak peek about the crazy things you've been doing over there?
Yeah, I'll give you a little bit of a push. So, in DesignCon last year, we introduced our very first water-cooled probe, and it was for power rail testing of high-speed optical transceivers. And it's been doing pretty well. But I just mentioned a little while ago that we have to have the ability to test these 2,000 amp power rails at package speed. And so we will be introducing, amongst other things at the Supercomputer Conference, the first 2,000 amp package speed refrigerated probe. And we'll see what it looks like when you bounce 2,000 amps in an ASIC package, and what that actually looks like on the board, and what noise margins really mean. And I will tell you that, I have it running here. It's eye-opening.
Wow.
And fun.
It's amazing the things that you do, Steve, but it's really fun to hang out with you. Right, Heidi?
Oh, it keeps me busy.
Yeah,
it's great stuff.
It tends to make a mess, and so I really do like the simulator. Simulators aren't messy, and you can make changes really fast. And when your refrigerators are leaking all over the bench, it's not nearly as much fun. But when you do succeed, finally, it's like,
yeah, right. Very satisfying.
Yeah.
Well, I need to let you both go, but thank you so much for this interesting conversation, and please come back.
That would be great. And thank you very much for letting us be part of the Ecosystem podcast.
It is my pleasure. It's my privilege, actually. To our listeners, thanks so much for joining us. I trust you really enjoyed this conversation with superstars Heidi Barnes and Steve Sandler. We'll see you next time. Until then, remember to always stay connected to the ecosystem.